Okay, so today's first half, today's lecture is going to be on metadata. Oh, got some, nope. Oh yeah, that's what we want. So first half is going to be on metadata, second half, data warehouses, and just dipping into the idea of data mining. Maybe we'll consider data mining and its relationship to what's called exploratory data analysis next year in the next block. But transitions. Right, metadata. So if we have data, but it doesn't have any context, it has, I'll put no value, but certainly reduced value. I think no value is probably a bit extreme, but if you think of the rawest data item that you could come with, like a temperature 25 degrees C, if you don't know where that was, you don't know when that was, that has no value whatsoever. But basically, the less you know about a data set, the less value use it has. So metadata is often described as simply data about data. And it's sort of structured information that describes the data set. Who created it? What the data set contains? What's it about? Where does it relate to? When was it captured? And how it was captured, that kind of information, that contextual information. And metadata is consumed by two kinds of things. One of them is people, who unsurprisingly like natural language, sentences, paragraphs, descriptions. But it's also read, some of it's read by machines, and of course machines function best on following some kind of formal syntax. Now machines can work on natural language, but they tend to be error prone. People can read formal syntax, but it's a strain and an effort. So some metadata is built for machines, some is built for people, but I would say probably most of it lives in a halfway house where some of it's for people and some of it's for machines, or it has a dual purpose. There's always that tension. So what do we use? What's the purpose of metadata, more generally? So it's a list of, I think I've got 4 different things here, what it's used for. There's probably more things that metadata is used for. If you've got any thoughts on that, that would be great. So one of its primary functions, if not its main function in many ways, is resource discovery, or its original function rather than prime function. Original was resource discovery. You need to find and understand resources, digital resources. We're talking, when I say resources, I'm referring to anything here. I'm talking about data sets, I'm talking about documents, I'm talking about digital objects, videos, anything like that comes under this heading of resources. Often they're called, in the literature on metadata, they talk about digital objects, digital resources. That's what they refer to. So identifying and understanding those resources, and as a consequence, being able to understand the difference between related resources and to bring them together to integrate them in some form or fashion. So discovering data is very important. The other function, so that's sort of a human function. Humans look for data, they need to understand it, see whether it's fit for purpose. The other thing is the machines, what the machines are interested in, which is interoperability, or more correctly, we are interested in the machines being able to be interoperable. So what do we mean by interoperability? Well, it's the ability for computer systems to exchange data, information, with minimal loss of both content and function. So I perhaps want to, I'm doing some statistical analysis, perhaps in the R statistical package. My data is in my Postgres database. can I get the information, the data out of the Postgres system so that I can analyze it in R? Can I do it with minimal loss? Can I get the exact data out? Well, for a database, for the case of a database, the answer is almost certainly yes. But do I maintain all the functionality that's available in the database when I'm accessing it through a statistics program or not? You almost certainly lose a degree of function, or it becomes more complicated to do things. Sometimes you can't do everything when you're connected to a database from another software. Sometimes it's just more difficult to do things. Sometimes it's more easy. Loss of content tends to happen with things like if you're being served data over the internet and maybe you're only getting perhaps a reduced resolution data set or something like that. Interoperability relies on systems implementing similar standards, not just metadata standards, but also the standards for actually storing the data themselves. But we're concentrating on the use of metadata. So it's not only, it's one thing is the using of common standards, and the other thing is if you don't use the same standard, do you have a mapping between those standards so that you can use that mapping to enable interoperability? The third use I've got there up here is digital identification. Maybe again, visit this again perhaps next year. So we're living in a world where we've got lots and lots of data. And not only do we have lots and lots of data, because people might download and make copies of that data and then perhaps do something with it to create a new data set, what might be called a value-added data set, we've got a problem in tracking where data sets have come from, perhaps, and what their lineage is, where they've come from. Also, increasingly with large databases, they are not stored in a single database server, but they're distributed across multiple servers, perhaps in a cloud-based environment. We're going to talk about clouds and what they are next year as well. So you may have different versions or different copies of the same data set being managed by a distributed database. And I think next week I will talk a little bit about distributed databases. It's not something I know particularly much about, but we'll look at them next week. And because of these multiple versions, whether they're within a distributed data set or they're copies within a group, it's useful to have a system. Well, for a distributed database, you need a system that uniquely identifies the items of data in the database and in the copies of the data, in the copies that are managed by the distributed database. And to do that, you need a unique identifier. And one form of unique identifier is called a GUID, a global unique identifiers. I'm sure you've seen these before. You might not know what they are. There are 128-bit values, which are often displayed as 32 hexadecimal digits like this, with a hyphenation in the middle of it. So that's if you software keys, if you've ever entered into a software key where you're entering some form of GUID type number into your software key sometimes. These are generated by a sort of random number generators. And it is possible, but very unlikely, that you'll ever generate or meet a duplicate GUID. So they're effectively unique, but they're not actually unique. I think I read that, now if I can remember the figures, it was something silly like if everybody in the world had something like 1 million GUIDs issued to them every day, there'd be a 5% chance of a duplicate being generated in a year or something like that. It's incredibly unlikely that you're going to get a duplicate. And GUIDs are increasingly used, and particularly in these distributed database environments, to identify rows. So instead of using a instead of using a sort of serial primary key or a primary key generated from your from other fields, like you do traditionally in the relational model, what is now starting to happen is that the people that are generating GUIDs and using GUIDs as the primary keys in their tables. And this means that you can identify, you've got a unique identifier for that row at a particular time in a particular place. And that allows them to maintain the uniqueness across distributed databases because they'll share the same GUID if you copy them and shard them across the data across different databases. GUIDs are also very useful because they're not restricted to the database environment, whereas your primary key identifiers are. If you want a GUID, you can generate a GUID anywhere you like, inside, outside a database, anywhere in a computer system you can generate. So programs can generate GUIDs, databases can generate GUIDs. So useful for identifying things. There's not only uniquely identifying the location of the rows in the data sets, or indeed individual data items, but the unique or the location of the data set itself somewhere on the internet. And to a certain extent, we're sort of meeting the internet before we've met what the internet is and what the World Wide Web is and things like that. And that's what we'll see at the beginning of next year, but we'll just work our way around that at the moment. So the location of a data set on the internet. So increasingly with data on the internet as opposed to data on local drives, how do you find an item on a document on the internet? Well, you use the URL, the Uniform Resource Locator. Your URL is your web address, or a web address is a type of URL. Okay, so it's what you type in your search in the top bar, the address bar on your browser to get to something. So it's usually HTTP, but it might be FTP for file transfer protocol. There's a number of other protocols and things that you might use as well. But think of it as an HTTP address or an HTTPS address. Now, the problem with using a URL to identify where something is, I'm sure you've all experienced, which is broken links. Broken links are very common. And as time goes by, people move jobs, etc., the breakages build up. So a URL, while it uniquely identifies where a resource is on the web, it has a tendency to break down. So there's a system called persistent URLs, PURLs, P-U-R-Ls, in operation, and I think there's a number of different ways that these operate. But what they basically do is they take a URL and then they redirect. It's like a lookup list, a lookup directory. So somebody types in. It doesn't redirect URLs particularly, or it might do. What it is a unique identifier for an object that then points to the most recent version of that object, or the current version of that object. So one system is called digital object identifiers that you might have come across, especially they're used particularly in by journals for identifying journal articles. You often have a DOI, digital object identifier, associated with them. So what the DOI organizations that maintain digital organization registries do is that they store a character string that uniquely identifies a digital object, which when you call that character string through the DOI server, returns the current URL. So basically it's a sort of clearinghouse for addresses, so that hopefully that your character string, as long as it's maintained and the person responsible for the data updates the URL that the DOI maps onto, you keep the DOI is constant, but where it points to on the web may change. So in this case, the metadata is the DOI, which points to our DOI resolver, which kicks out the most current URL. So it provides one unique identifier for the location of a resource on the web, but it still requires the person managing the data to keep the URL up to date. Fourth thing that I've got listed here is archiving and preservation of data. With computers, it's so easy to make copies of data, to manipulate data. It's sometimes easy to forget that digital resources are in fact fragile objects. They degrade like everything else through time. Hardware degrades, it gets old, it breaks down, it's thrown away. Software that was written 10, 15 years ago can now be difficult to run because the operating systems are historic, they may not be maintained, the code. Now there's quite a lot of emulators available so you can run, say, Atari code from 30 years ago in an emulator within a PC, but that's actually just a sort of relatively recent development. So there is sometimes a real problem with data that's held on particularly old hardware, programs written in old software. So I think it's a few years ago now, but maybe 15 years ago, when I worked at Portsmouth and I was trying to do a little bit of work with a guy at Queen Mary, and he had a satellite image that he'd used during his PhD, another 10 years before that. It's the only time I've ever been handed data on one of those large tapes that you see in the sort of 60s movies that you stick onto a machine that goes round and round like this, a double tape thing. And it took us months and months before we found the machine that we could actually extract that data from and then work out what format it was, because it was in a format from 20 years previously, to upgrade that data and get it into a modern system. So this is a real problem, and also, of course, there's always the danger of corruption occurring, especially with physical disks and things like that. You can always get corruption, and then when you've got databases changing through time, you've got to potentially preserve time slices or have some way of being able to see a data set as it was at a particular time. So these are some of the things that metadata is used for. It's probably used for many other types of thing as well. Okay, so what does metadata actually look like? What's the sort of what's it composed of? So this list comes from this web address, the DCC. I can never remember, data something centre for the UK. Basically, it's the UK centre for metadata, for all sort of things to do with metadata. And they call their list functions of metadata, but I think they're better described as categories of metadata. To me, the functions of the metadata is what it helps you to do. But these are the categories, 5 categories of metadata that are identified in this web paper. Descriptive metadata, technical metadata, administrative, use and preservation. Descriptive data, so we run through these really quickly. So descriptive metadata is what you probably think of as metadata on a daily basis. Data about data, also referred to as content about content. It describes the data set and the individual items of data potentially. So this is your discovery metadata, metadata that tells you what this data set is and hopefully gives you an idea about what it's fit for purpose for. So it contains simple information like title, an abstract that describes the data set, gives an overview, the author, various keywords, things like that. and uses, particularly for things like keywords and authors, uses a lot of controlled vocabulary. So controlled vocabulary is just a list where you choose one of the items from the list. So rather than having free entry of keywords, select keywords from an available list of keywords. So they tend to quite often use controlled vocabularies. Technical metadata is data about the containers of data, the schema design, the format of the data. And that's both useful to humans, programmers who want to write code to access the data in a particular format, but it's also used a lot by machines. Machines, if they can automatically understand the schema of the data in a database, then they can potentially automatically do something to process that data. So technical data has both functions for both the human and the machine. It also details potentially the technical processes used to create the data, and perhaps some kind of technical requirements to use the data. This data is in this format, it's in an ArcFile geodatabase, therefore you version whatever, therefore you need ArcGIS version whatever to be able to read this. Oops. Oh, I hate these transitions. Okay, administrative metadata, a third one. So this is all about the management of the digital objects. Things like intellectual property rights, license conditions, how to cite the data. Also things about version control. How often is the data updated, for example? Is it updated once a year, or is it a rolling update and you're downloading the data from a particular day at a particular time? Use metadata may be stored. This includes things like controls on user access, who can access the data, who has the permissions to access the data, and tracking the use of the data by users. Do you need to register on a data website? Does it then record whether you have downloaded a particular data set, what date you downloaded it, that kind of stuff. User tracking. Also, if you've got different versions, it may track which version obviously is being used, which versions are being downloaded. And the final form of category of metadata is preservation metadata, which contains information on the actions taken or should be taken to preserve a digital data object. Migrations between versions, between database, perhaps between different database schemas, checksums, which are basically, I've never really understood them. They're numbers calculated from data sets, and they basically, if you get the same number calculated from two files, you know that those files are the same, basically. That's the way I understand checksums. Sometimes when you download something from the internet, it'll say, do you want the checksum, to check the checksum value to make sure the data has been downloaded completely. So things like checksums and things like the physical information on the physical media that the data is stored on, as I say. One day you might meet something on some kind of ancient tape or something like that. Even floppy disks are now incredibly difficult to find a floppy disk reader. I'm sure you can go and buy one on the internet, but you try and find one just easily. You need one in 5 minutes. You're not going to get one in 5 minutes. Metadata can exist at a whole variety of levels of aggregation of your data. So in a relational model, you might have metadata that describes the database as a whole. This database contains this set of information, this set of data. Part of which is the list of tables and the metadata that describes each table, potentially. Then there may be information at the level of the record. Who collected this data record? Who entered it? When was it entered? that kind of thing. Then we could have metadata at the level of the attribute, as in the columns of the table. So one could say that's potentially subset of that, but so we might want to know exactly how temperature was recorded in that column. And then we might have metadata at the level of the individual value. This was measured, the temperature was 25 degrees C, but the weather station had been vandalized, so this was taken with a handheld digital thermometer as opposed to the full weather station. So that may be at the individual value level. So you can have metadata at any of those levels. And you can also have metadata that describes the relationships between any of the above. So it can be pretty extensive metadata. Two basic approaches to storing metadata. You either embed it within a digital object, and this tends to be the case for particularly metadata that's designed for machines rather than humans. Because with a human, you've got to open up the file, get the find where the metadata is in the file header, understand it. But so this tends to be for machine reading. So for example, the EXIF exchangeable image file format or metadata format can be embedded in various image files, including JPEG, PNG, TIFF, I don't know what GIS ones are, and also sound files. So I imagine if you take a photograph with your camera and it records the time, maybe the geolocation of something, this is where that information is often stored in this sort of EXIF format. Also think, embedded in the digital object, have you come across header files for ArcGIS rasters for importing? There's an example of well, actually that's a separate file. Sometimes you can get the headers embedded in the raster import file. Sometimes you get them in a separate header file. Also, another place where you find these, another example of embedded metadata is HTML header tags, and we'll meet those next year. And they contain metadata on HTML web pages. The other way is to store the digital object or your digital metadata record separate from the digital object as a database record, or often as an XML file. And when we, again, XML, we're going to see XML a lot next year. And metadata schema are sets of metadata elements, or fields as we often call them, but in the metadata language they tend to talk about elements rather than fields, designed for a specific set of information resources. So, and those schemas, they're analogous to a database schema. They define the metadata elements themselves, the fields of the metadata, which contain the semantics, the meaning of the metadata. And then we have what are called element domains, just like database domains. They set ranges on the content that can be put into these elements. So ranges of acceptable values, controlled vocabularies, and sort of syntax rules. Does it have to be in what rules for capitalization and stuff like that? And then the third thing that they define is the syntax of the elements themselves, their ordering, how they're presented, the hierarchical relationship between the metadata elements, that kind of stuff. And those are actuated in file formats like XML, GML, RDF. Now those probably mean very little to you, but we'll meet those again. So that's on one metadata schema. Anybody can devise a metadata schema just like anyone can devise a database schema. But sharing is good and makes life easy. both for discovering metadata and for interoperability between software products. So therefore, unsurprisingly, metadata standards have been developed, which are basically an agreed, community-agreed metadata schema. So an example, and a kind of crucial example, is called Dublin Core. Dublin Core is a metadata standard that's been defined for digital resources, full stop. All digital resources on the internet. It's meant to be the overarching metadata schema for all digital objects on the internet. Why is it called Dublin Core? Well, it came out of a 1995 workshop in Dublin, Ohio, organised by a couple of American institutions, data centres. And it's managed by the Dublin Core Metadata Initiative. And it contains fields, it defines fields like title, creator, subject, description, publisher, contributor, whatever that quite means, date, type, format, identifier, etc., language. So these are things that apply to many, many different types of digital objects. They can be documents, they could be images, they could be geospatial data files, they could be just about anything that you can imagine putting on the internet. That is the job of Dublin Core, to provide one description for everything on the internet. There are also many domain-specific standards defined. So for geographic data, one could say the international standard is maintained by the ISO 19115, which is an international standards organization, metadata standard for geographical information, meant to be a global standard. Then, as we go to Europe, Europe has a project called Inspire, and I imagine some of you are familiar with Inspire, perhaps, those who work at councils. Anybody had contact with Inspire? No, okay. Inspire is the European effort to provide a geospatial metadata standard for the European Union so that data can be brought together at the European level for European EU reporting. Then, in the UK, now I imagine some of you are familiar with Gemini. Gemini? Is anybody? No. That's interesting. It's interesting. I thought you'd know more about Gemini than I do. So in the UK, the geospatial standard is called Gemini, which is maintained by the AGI, the Association for Geographic Information, which is a UK body of that represents the geospatial industry. Both producers, consumers of data, universities and things like that. So we've got a global standard, a European standard, a British standard, and the GDC is the American standard for the federal government, the American federal government. And I could produce probably a list that went over several dozen slides if I had the inclination to do so, which I don't. So those are examples of geographic data metadata standards, but there are also metadata standards in many other disciplines that include geographic component. So two that I'm familiar with are the what's called ecological markup language, EML, which is a metadata standard for ecological data, some habitat data, stuff like that, abundance time series information, stuff like that. And that contains geographic information. Where does this data relate to? So it shares some things with these standards. Also, museum natural history specimens use a standard called Darwin Core, which is specifically related to natural history specimens, but also includes a geographic component. Where was this specimen found? So how do these relate to each other? Well, Dublin Core is the mother standard on the internet. It's the most general standard. Other standards add new new elements because they're more specialized, just like subclasses in the object model are more specific than the more general superclasses. So doubling core is like a superclass, and the other standards are like subclasses. But they add new elements in that's related to the particular domain that they're interested in. But they don't just add new elements willy-nilly. You only add a new element when you really need a new element. And otherwise, you should, wherever possible, standards tend to reuse elements from other standards wherever possible. So there's a lot of cross-fertilization between these. So EML may share some fields with, say, EU Inspire. It may borrow some fields from Inspire for its geographic definition. Yeah, okay, so that's just a list of some of the organizations that in the US that maintain and sign up to the FGDC standard. Clearly, the more organizations, the more people use the same standard, the better overall for the integration and discovery of data. And just these are the 10 categories. I think we'll just skip over these. So really, I just included this list to show that you can divide those fields up, those elements, in many different ways. You can classify them in different ways, unsurprisingly. And this is just how the FGDC classifies the various elements or groups of elements in its data set. So things to do with the identification, data quality, spatial data organization, etc., etc., etc. I don't think we need to go into any of those. So, about 10 minutes before coming in over here, I discovered that UK Gemini, which is the UK geospatial standard, is now, the latest version is 2.2, not 2.1. I just discovered that about 10 minutes ago. Not that matter. Okay, so this is 2.1, and this is this table summarizes the 43 fields of the UK Gemini geospatial standard. Now, I'm really surprised that councils, maybe it's just that your job doesn't involve this, but I'd have thought councils would have been capturing data in UK Gemini standard, and I'd be interested to know who's using it and what for, and if not, why not. So here's our list of elements, element number, and then we've got the list of whether they're obligatory or whether they're optional, and then we've got a list of how many occurrences, basically the cardinality of the element relationship. So you can only have one south-bounding latitude, one north-bounding latitude, but you can have many extents, perhaps if you've got disjunct surveys or something like that, spatially. So some of these elements you can have many of, some you can just have one of. And we'll just look at a few of these in detail. Title, the name given to the data resource. Important things, well, one of the important things I want to show you on these is that the definitions, you've got the equivalent mapping onto the EU Inspire metadata standard, but of course the data being captured, metadata in UK Gemini, is being fed up to Inspire, so it's really important that you get a good mapping between Inspire at the European standard and Gemini at the UK standard. But for various reasons, these things are not always perfect matches. Historical reasons, for example. Perhaps the UK defined data standards before the ISO standards were defined. Maybe we just disagree with the ISO. So here we've got the equivalent ISO element. It's called MD data identification dot citation. It's equivalent as well. Obligation, mandatory, single occurrence. It tells us it's a character string. It's free text, so it's chances are it's human readable. No change from previous versions. So that's a very straightforward one. Category. This is an example of one with a controlled vocabulary. It's got a number of, let's see, where is it? Class. Data type is a class. So this is an example with select one or more categories that most closely represent the topic of the data resource. So this is, it's to do with demography, it's to do with environment, it's to do with habitat or something like that. So you've got a list of possible topic categories, keywords that you can associate with your metadata item. There's our list of categories for the Gemini. So there we go, society, structure, transportation, environment, economy. It's up to the person defining the metadata record to decide which of these are appropriate for a particular data set. And of course we have the, we always have the human side of things. Ooh, we went right, oh dear. We always have the human questions. This is an old, this is not the correct version of this. Okay, so make sure that, does the same person in different organizations select the same set of keywords for the same data set? So there's always that human component. Are people interpreting these categories in the same way in different organizations? Extent, geographical, just the bounding box. But also, for let's see, is this an EX extent? So it's either going to be a spatial extent, as in coordinates, or a polygon, but it might also, I think, be a description like Northamptonshire or something like that. So you might, so in certain fields, certain data elements, sometimes it's hard, it's numeric data, but it can also be descriptive text sometimes. Lineage. Lineage is a free text that describes the events or source data used in the construction of the data resource. It's basically how it was made. Now, this is, at the moment, tends to be free text. It's just a textual description of how data sets were created. Now that's all very well. Whoops. Oh dear, we've got a bit out of sync here. Okay, that should have been before. Never mind. So lineages, lineages are how a data set was created. Things like, so one could informally describe in natural language, we did this, we did this, we did that, we blah, blah, blah. However, wherever possible, it's better to provide a formal workflow model. Are people familiar with ArcGIS Model Builder? Basically, it's a graphical environment in which you can drag and drop ArcGIS tools, you connect them together, and you can make what's called a workflow. It's basically graphical programming. So in a GIS environment or in a workflow environment in which you basically write a program that creates, that generated the data set that you're describing with your metadata, this provides an absolute formal description of the process of creating that data set. Okay, so you've got your inputs, your data inputs at the beginning, and then you've got the process that was used, the full description of the process that was used to describe that data, how it was created. And for machines, both machines and for humans, it's really helpful to have that. For machines, that automatically gives you the process in a computer, in a formal description of the process used to create the data set, which is also useful for human beings. So it would be great if we could incorporate these workflows into the metadata lineage. And there are efforts to do this. 2008, it's quite a long time, you know, we're getting on now. I haven't come across, I think we're still developing these standards and ways of incorporating these lineage models into metadata, into formal metadata. They're still working at that. They're still trying to develop these. So that's an area of active development. All right, I'm just going back up to my cartoon, which was a bit out of sync. So we were talking about these different metadata standards. Well, why are there all these different metadata standards? So in the cartoon, there are 14 competing standards. We need to develop one universal standard that covers everyone's use cases. Situation, there are now 15 competing standards. Why are there different standards? Well, people have different needs. That's one reason. People have decided they have different needs. So the ISO was an international attempt to bring everybody's needs together across the planet. We decide we have slightly different needs in the UK, therefore we add additional fields, things like that. And then there's just history to a certain extent. The Americans developed their system, the Europeans developed their system. So there is a proliferation of standards, but to a certain extent, only a certain number of them are extensively used. The take-home message is you're unlikely to ever come up with one standard that meets all people's needs everywhere. Don't attempt it, don't bother with it generally. Having said that, the Dublin Core is a very example of one standard that attempts to cover all digital objects on the internet, but it doesn't intend to be and enforce that and to be a set of rules for all digital objects. It's just the general set of fields that are appropriate for most digital objects on the internet. And therefore other standards borrow those fields from Dublin Core and from other standards. Right. Metadata in databases. So where do we actually store this stuff? Well, you can store it in database fields. It's just data. You can store it in a database field. You can make fields, tables to store the metadata. And that's often done. But there are other alternatives. As I've mentioned, a lot of data, metadata, is stored and transferred in XML. What is XML? This is XML. If you've never seen an XML file, it's basically a set of tags with content embedded within the tags. And we're going to meet XML in detail next year, I keep saying. So here we are, we've got a metadata, we've got a citation, there's its information, origin, Canadian ICE service, publication date, 2008, and then a description abstract. So this is our schema, this is our metadata schema. The tags, the order of the tags, their definitions are the metadata schema, and then you need additional rules that go on top of that to define what goes within each of these, between these tags. So a lot of metadata is stored and used in XML because of it's quite hierarchical. These elements, you have these one-to-n relationships, these parent-child relationships, which are not represented well in your relational database, but are modeled quite well in XML just through the hierarchical structuring of tags in your XML file. So a lot of metadata databases store the XML rather than breaking it apart and storing it in it's still stored in tables in a relational database, but it's stored as XML in tables. So organizations might build, and often do build, an XML database to store their metadata, and a lot of metadata is stored in these XML databases. Why do you do this? Well, as I say, there's the hierarchical, deeply nested aspect of metadata. It's not particularly deeply nested, but once you get a couple of levels of nesting, the relational model has trouble. Organizations have a lot of data in standardized XML already. They've captured it, it's been organized into XML. Why take that XML, have to write conversion programs to store it in the fields of a database, and then possibly extract it back to XML again to distribute over the internet? So why double model? What's the benefit in double modeling? We've got a model in XML, why have a relational model of the model that exists in XML? So especially if data is being produced in XML, consumed as XML, why not just keep it as XML? XML also has the advantage that it's quite human readable, although once you get a big XML file, you might regret trying to read it. How does it store in the database? Well, there's a whole variety of different models, data models for storing XML in a database. One method is to basically have a very large character object. You take all the XML, this is just a text file, a text editor, you store it all in one large character object, then you use string parsing functions to extract the values from between tags and things like that. There are also systems that shred the XML into various subgroups, which stores in the tabular structure in your relational database. So it kind of takes chunks of these bits and stores them separately. And then there is what's called a native XML format defined by ISO, whatever. I know very little about these, but it's a particular database format that allows you to store these whole XML files. ArcGIS, just as an example, a couple of examples of metadata. How do you actually edit these stuff? How do you manage this stuff? So in our catalog here, you can highlight a data set, and then if you go onto the description tab in catalog, you get access to the metadata fields. And this is a raster data set that I've got here. As you can notice, I've entered absolutely no metadata for this item. The only values that are added in are the extent, which are automatically extracted by ArcGIS from the data set itself. Okay. So here we can enter in, we can press the edit button, and we can edit the metadata in here. So ArcGIS has an embedded, or ArcCatalog has an embedded metadata system. And if we go into the options, we can set which type of metadata schema, whether we want to cover. So we've got the Inspire, we've got the FGDC, we've got ISO 19131, and we could add in a schema, say UK Gemini, into that quite relatively easily. There are also a whole load of standalone or web-based metadata editors. So I found this morning, UK location metadata editor. I didn't download it. I'm not sure whether it's a web-based system or whether it's a program that you download and install, but it's an editor that allows you to capture the data in the UK Gemini format. All right, we'll run over a little bit, and then because the other section's quite short. Metadata is data. Don't forget that. It's nothing special. It's just, it can be used as data. So here's an example. This is taking the metadata from research articles, the authors, what departments they work in, that kind of thing, and then taking from that information on tens of millions of scientific papers, then using the connections between the authors and what they publish in and what the keywords associated with the journals, the Cathy Bonner at Indiana created this map of science. So these are basically, these dots represent groups of papers and where they lie. This has been sort of it's a sort of clustering network algorithm they've used. So it shows the relationships between various disciplines. So we can see the strong connections between the earth sciences and biology, infectious diseases, medical supplies, brain research, etc. Humanities, quite off on their own down here compared with maths and physics over there. And important to notice this maps round onto the other side. It's like a globe map. So here we're using the metadata on the citation for the citations of papers to produce a map of science and the relationship between scientific disciplines. We can take a similar set of data. This is not the same data set, looked at a different way, but a map of scientific collaboration from data from Science Matrix, a company that monitors research groups. And this has taken the spatial metadata, plotted it out on a map to get a a visualization that allows us to see the connections between, the geographic connections between research groups across the EU. I can't say it tells us anything particularly informative. Clearly we can see that the degree of collaboration decreases as we go further into Eastern Europe. We can see the main core, we can see strong degrees of collaboration in the Benelux countries and down to Strasbourg, the border between France and Germany, things like that. But nevertheless, we can make maps from the metadata. So we're going to end with a little story on this section. Tom's, Sidesma. So, metadata has been in the news from the security perspective. Laws, the security services have had or get permission to monitor what we're all doing in our lives. But they're only allowed to access the metadata rather than the data, the content we're actually looking for it. So this is an experiment by Tom Sidesma and colleagues where they installed an app onto this guy's mobile phone that collected the same type of metadata that the security services are collecting on at the moment, potentially on all of us. Simple things like phone usage, email header information, and the geolocation from the mobile phone. So what happened in 1 week? Well, the people who analysed the data afterwards, who didn't know anything about this guy, didn't know who he was or anything, didn't know his name was or anything, they managed to extract 15,000 time-stamped records from 1 week. Every time he made a connection with a communications tower, sent an email or visited a website, we could see when this occurred and where he was at that moment within a few meters. They inferred his social network based on his phone and email traffic. They saw the sites from his browser data. They saw the sites he visited, the searches made, and we could see the subject, sender, and recipient of every one of his emails. So what did they find about this guy? Well, general. He's a recent graduate in his early 20s, receives emails about student housing, part-time jobs, etc., etc. So basic things about his life. He often doesn't get home till 8 in the evening. Once at home, he continues to work late. They didn't quite sure whether he lived with his girlfriend, whose name was Meryl, but they did know that they were in a quite serious relationship. Up to 100 WhatsApp messages a day. How does the man do any work? They're quite incredible. He reads Scandinavian thrillers, or at least he searches for those titles on Google and Yahoo. So, a whole load of stuff that if we look at it from a commercial lens, so that information could be used for targeting marketing for him. We know the kinds of things he looks up. So if we were a company like Groupon or WE Fashion, whoever they are, or computer stores, we may be barraging him with unwanted, unsolicited junk mail as a result of having seen his metadata, what his metadata profile. We learn that about his political leanings. He sympathises with the Dutch Green Left, although he's regularly in contact with other political parties as well. They find out that he works, the type of work that he does. He frequently sends messages using in encrypted software. He works with databases, spends time on technology forums about data registration and processing. So he obviously works in a computer-related job, and he keeps up on news about hacking and roundup of child pornography. So we're getting closer to what he actually does in life. Well, they actually work out, he works as a lawyer for the digital rights organisation Bits of Freedom. So they get a good profile, they know where he works, and they know pretty much what he does in his job. Then they grabbed a file from Adobe, a hacked list of user emails, 150 million user emails from Adobe. This woke me up when I read this the other day, and I'm going to change my security behavior as a result of reading this. So they matched those they got this list of passwords from Adobe. These are all encrypted, but if it's the same password, then the encryption is the same. So they looked through these various encryptors, and they saw that a number of other users in the Adobe had the same password as this guy had. They then took a look at the hints for those users, found these various password hits, Another Day in Paris, and they laid them to his password. So Tom Sidesman's favourite band is Strung Out, and the password Strung Out was used, so they'd broken into his Google Mail account, his Amazon accounts, hacked access to his financial, they could buy things on Amazon, had access to his credit card details. And that was just using one item of additional information. The security services clearly have access to many, many other items of subsidiary information that can be brought together. So that's a sort of salutary message to me personally, actually, as I say. I think I'm going to change how I deal with passwords on the internet as having read that story. Not particularly that I've got anything to hide, but I'm not unduly worried about the security services. I'm more worried about criminals than the security services, but that's a personal thing. So just to finish off metadata. I love this. Metadata is a love note to the future. I think that's a really sort of poignant description of metadata. Metadata, you write metadata, the person who writes the metadata is often the person who has the least interest in it themselves. Although that's not strict, one should be careful about that, because I created data sets maybe 20 years, 25 years ago. And if I haven't got good metadata, how good's my memory for 25 years ago for what I did? So it's a love note not only to others, potential users of the data, but to myself, potentially in the future. Because if you don't look after if you don't maintain the metadata, the usability, as we go right back to the beginning, the usability of the data is greatly reduced. And when's data used? Well, it's used in the future for many things. You don't know when you create a data set and make it available to others what they're going to use it for. So without that good metadata, the usage of your data is going to be limited. All right, we'll have a break there. And then the second section is quite short.